I'd like to look at a few more examples in this section. It's a relatively short section, but we'll look at a few more examples in this video. First, I would like to find the area bounded by y equals x squared and y equals 9. Hopefully you look at this problem and it's a little bit different from the last one that we did. It's a little bit different because we don't have an interval to work with. They're not giving us an interval. So that means that we're going to have a little bit more work to do. So I'm going to graph these two functions first just to get an idea of what they look like. So let's see, I should have y equals x squared. That's a parabola that opens upward. Let's see, y equals x squared. It looks something like this, horizontal tangent line. Here's y equals x squared. And then you have y equals 9. That's a constant function at 9. I don't want to be too specific about, details. I just want a general idea of what these look like. I want enough of an idea to tell me, here's what the area looks like, and then I can determine what's my upper function, what's my lower function. I don't need to know exact points. So this blue constant, that's y equals 9. And we're looking for the area bounded by these two functions. When we say area bounded by those two functions, we really mean the area contained between those two functions. So the area between x squared right here and y equals 9. That's talking about this area right here that I'm highlighting. So I can kind of look at this and say, okay, maybe we have a feeling at this point we can kind of draw in our vertical line and say, okay, here's my upper curve, that's the blue curve, y equals 9. Here's my lower curve, it's y equals x squared. So you could actually set up your integral at this point, I think. You could say, this is my upper curve we said was y equals 9, minus my lower curve is x squared. The only thing we're missing now, these limits of integration. What should our upper and lower limits of integration be? So we have a little bit of work to do because we want to know, okay, really, where are these two functions intersecting? So what I'm going to do is take these two functions and just set them equal to each other. So I'm going to take x squared and set it equal to 9. And when I solve this equation, it'll tell me exactly what x values these two functions intersect at. So this one's pretty nice to solve. I just take the square root of each side. I end up with x equals plus or minus 3. So that means it intersects over here at positive 3, and then on the left-hand side at negative 3. That also means that these are the limits of integration here. So my limits of integration will be from negative 3 to positive 3. So here is the definite integral that I'd like to evaluate. From here on out, I don't really need to look at my picture or anything else. I know that I'm just evaluating this definite integral. So first thing I need to do is I need to find my antiderivative. This would be 9x minus x to the third over 3, evaluated at 3 and negative 3. So let's see here. I have 9 times 3 minus 3 to the third over 3 minus 9 times negative 3 here minus negative 3 to the third over 3. Careful with your signs. So let's see, 9 times 3 here, I've got 27 minus 3 to the third, that would be 27 divided by 3, that's 9. Minus over here, 9 times negative 3 here, I have negative 27. Minus negative 3 to the third would be negative 27 divided by 3 minus negative 9. And so, okay, 27 minus 9, that first term, let's see, 27 minus 9, I've got 18 minus negative 27 minus negative 9. We say minus a negative, that's really plus a positive. So negative 27 plus 9, I have another 18, but this time a negative 18. 18 minus negative 18, that is 36. So the area bound by those two functions is 36 square units. So if we're not given an interval, that picture becomes extra important because it really does help us figure out where our functions are. It helps us determine what our region is, kind of where should we be looking, and then it might also help you kind of check your answer here when you find those points of intersection, because those are going to be a big part of our problem. It determines our upper and lower limits of integration. Let's look at another similar one here. This time I want the area bounded by f of x equals x squared and g of x equals square root of x. This one's pretty tricky to graph. This one you would probably need a graphing calculator for, or I think Desmos would be a really helpful tool for you to use. I'm going to go ahead and sketch this in. So if you were to look at y equals x squared, you would see a parabola which opens upward, and actually I'm going to exaggerate the features here just so that I can see the area a little bit better. So this is f of x equals x squared, and then g of x is square root of x. Now if you graph it on your graphing calculator, you're going to have a hard time seeing it at first. You will have to zoom in a little bit, but when you zoom in, you'll actually see square root of x looks something like this. And we're looking for what is this yellow highlighted region right there. So here is my g of x. So here, again, I'm not given an interval to work with. So I'm not given an interval, so that means I need to find where these two functions intersect. It looks like they intersect right here at 0, and that's one you could probably go and check. But what is this other point right here? What is this x value? So I'm going to take x squared, set that equal to square root of x, and solve for x. This one's a little bit tricky, I think, to solve. It's not quite so straightforward. I don't like square roots, so I'm going to get rid of that first, and the way I'm going to do that is I'm going to square both sides. X squared squared, when I have a power raised to a power, we multiply those two, so I should have x to the fourth is equal to x. Now be careful here. You don't want to divide by a variable here, because that means you're going to lose out on a root. You're going to lose out on a solution. So what I'm going to do instead is I'm going to set this equal to 0. So I'm going to subtract x from each side. It'll give me x to the fourth minus x is equal to 0. And now I see, hey, both terms on the left-hand side, those are factors of x. I can just take x out from each factor. That'll leave me with x cubed minus 1 is equal to 0. And so I have two solutions. The first is just x equals 0, which that one we said, okay, we're going to have that one for sure. The other one I have x cubed minus 1 is equal to 0, which gives me x cubed equals 1. If I take the cubed root of each side, I end up with x equals positive 1. So that is my other point of intersection, x equals positive 1. So here, when I set up my definite integral, I know I'm going to be integrating from 0 to positive 1. Now I just need to determine what is my upper function and what is my lower function. So again, if you need to draw in that vertical line, I do think that helps you determine what your upper function is. Here, my upper function, the ceiling of that region, is the blue function g of x, which is square root of x. So let's write that as square root of x, minus my lower function is the black function f of x, that is x squared dx. So I'm just trying to evaluate this definite integral. And I know I'm going to want to integrate square root of x, so I'm just actually going to take a second and say, you know what, let's just write that as x to the 1/2 right away. So let's see, I want to find my antiderivative first. So that would be x to the 3/2 power multiplied by the reciprocal would give me 2/3. Minus over here, I should have x to the 3rd over 3, or 1/3 x cubed, evaluated at 1 and at 0. So let's see, I should have 2/3 times 1 to the 3/2 power minus 1 cubed over 3 minus 2/3 times 0 to the 3/2 power minus 0 to the third over 3. Here on this right-hand term, 0 to the 3/2 is 0 times 2/3. That's just going to be 0. And 0 to the third is 0 divided by 3 is 0. Be careful with this. This is just a friendly public service announcement. Don't always assume that if you plug in 0 to your function or your antiderivative, you're always going to get back 0. That's a very easy way to make a mistake. You do need to take that x equals 0 and plug it in just to make sure. If it's a polynomial, yes, but if it's anything other than that, then we cannot make that assumption. So just be careful, make sure that you're not skipping that step. So let's see, 1 to the 3/2, that's just 1, so I have 2/3 times 1. Oops, 2/3. Oh boy, this is just a mess. 2/3 times 1 minus 1 cubed is 1 over 3, 1 over 3. So I'm left with 2/3 minus 1/3 gives me 1/3. So the area bound by those two functions is 1/3. Very cool. Last example that I'd like to talk about here, I would like to find the area bounded by y equals x cubed plus 1 and y equals x plus 1. This one I do think is pretty tricky to graph, so I'm going to go ahead and graph it again. But you may want to just hit pause on the video and see if you can try graphing that one for yourself, just to see if you can do it. If you can graph this one, I think you'll be good to go. And of course, yes, you can use your graphing calculator to help you. What you would see if you graphed these two functions, oops. Think about this, y equals x cubed plus 1. That's just the cubed function shifted up by 1 unit. So you would see something that looks like this. And then y equals x plus 1. That means let's see, for this line, my y-intercept is 1, my slope is a positive 1. It's going to look something like this. And I have a new and interesting problem to worry about here. I have this shaded region to find, and I have this shaded region, and I'm not sure what are they talking about here? They didn't give me an interval. So here's an instance where I do have to use two separate definite integrals. And I had alluded to this earlier when I said, hey, we need to worry about that point of intersection. Because if we have a point of intersection, like we do here, we have to break this up and we need to write two separate definite integrals. Because if you look, the upper and the lower functions switch. On the left-hand side over here, the upper function is the black curve, the lower function is the blue curve. But if I jump over to the positive x-axis, there it switches. Now the upper curve is the blue curve and the lower curve is the black curve. So we want to make sure that we split this up. We're going to need two separate definite integrals. So let's find our points of intersection first. Because they didn't give us an interval to work on, we do have to find the points of intersection. So I'll take x cubed plus 1, set that equal to x plus 1. Well, if I subtract 1 from each side, that's going to cancel. And here again, I know I don't want to divide by x, so I'm just going to set this equal to 0. So we'll subtract x. That gives me x cubed minus x equal to 0. Here I can factor out an x. That'll leave me with x times x squared minus 1 is equal to 0. Over here I end up with x equals 0 and x squared minus 1 equals 0. Solving this gives me x squared equals 1, or x equals plus or minus 1. So I have x equals 0 and x equals positive and negative 1. And this hopefully makes sense if we're looking at the graph. We actually have 3 points of intersection. We've got a point of intersection right here at negative 1. We've got a point of intersection right here at 0. And we've got a point of intersection here at 1. So I'm going to need, I said, two separate definite integrals. So let's break this up. Let's talk about the left-hand side first. On the left-hand side, I'm even going to write left side. On the left side, we have, let's see, where our interval would be -1 to 0. So -1 to 0. There, my upper curve is the black function. Remember, we said that was x cubed plus 1. So my upper function is x cubed plus 1 minus my lower function is the blue function, that is x plus 1. So I'm going to start with this. And then whenever I find that, I don't necessarily have to do both of these at once, but I want to show what we end up doing here. Eventually, I'm going to want to add the integral for the right side. And let's just set that up so that we have it. So let's see, that interval is 0 to 1, but this time my upper and lower function have switched. Now my upper function is this blue line right here. So now my upper function is x plus 1 minus my lower function, that black curve, that is x cubed plus 1 dx. So this is my right side. So I'm trying to evaluate these two separate definite integrals, and then once I have the results, I'll just add them together. So let's work with the left-hand side first. I'm just going to rewrite the problem down here, -1 to 0. We had x cubed plus 1 minus x plus 1 dx. So first thing we'll want to do is distribute this minus sign. Make sure that you're using parentheses here because I do want to distribute that minus sign to both terms. So here I should have the definite integral from -1 to 0. X cubed, 1 plus -1, these two will cancel, so I just have x cubed minus x dx. So let's see, I want to find my antiderivative. This will be x to the 4th over 4 minus x squared over 2, evaluated at 0 and at -1. So this will be, let's see, 0 to the 4th over 4 minus 0 squared over 2 minus -1 to the 4th over 4 minus -1 squared over 2. So here 0 to the 4th over 0, that's just going to be 0, and 0 squared over 2, that's just 0. So I have 0 minus, let's see, -1 to the 4th, that'll be a positive 1 over 4, minus here, again, I'll have a positive 1 over 2 this time. If I get a common denominator, I've got 1/4 minus 2/4, give me opposites -1/4, -1/4, which would be a positive 1/4. So, okay, I've done a lot here, but that means that the definite integral on that left-hand side, this has a value of 1/4. So now, I just need to find the definite integral on the right-hand side. So let's scroll down so that we have enough room. This time I'm going to integrate from 0 to 1. We said our upper curve this time was x plus 1 minus x cubed plus 1 dx. Again, make sure you're using parentheses here because I want to make sure to take this minus sign and distribute that to each term. Because that's what tells me 1 plus -1, those two will cancel. So this time I'm left with the definite integral from 0 to 1. I've got x minus x cubed dx. This should look pretty familiar. So I have x squared over 2 minus x to the 4th over 4, and I'd like to evaluate that at 1 and 0. So let's see, I've got 1 squared over 2 minus 1 to the 4th over 4 minus 0 squared over 2 minus 0 to the 4th over 4. And once again here, 0 squared over 2, that's 0. 0 to the 4th over 4, that's going to be 0. Please make sure you double check your work and make sure that that is the case. Here we're working with a polynomial, so it is. We don't need to worry about it. And let's see here. I've got 1/2 minus 1/4. We looked at this earlier. We said this is 2/4 minus 1/4 or 1/4. So hey, 1/4 once again. What do you know? Who could have guessed? So that means that the right-hand side is also 1/4. So now I'm saying 1/4 plus 1/4. Well, that's really 2/4 gives me a total area of 1/2. So once I add these two together, that gives me the total area bound by those two functions. That's what gives me that yellow shaded region in my picture up here. The two yellow shaded regions together have a combined area of 1/2. So this one is very tricky. I won't ask anything like this on the exam, but it is important to make sure that you check for those points of intersection, because if you have more than one point of intersection, or if you have a point of intersection in your interval that is given to you, then you do have to split that up into multiple integrals. So just something else to keep an eye out for. And that's all I got for this section. So when we come back in Chapter 7, we'll actually be done with integrals for right now. We're going to come back and we've got one last hurrah for derivatives. So we're going to jump ahead and start to talk about three-dimensional functions and partial derivatives in Chapter 7.